Okay, today I'm going to talk about AnonRep towards tracking resistant anonymous reputation system. This is a joint work with David Walensky, Richard Chen, Ivaseta, Chao Teng, and Brian Ford. On today's internet, we have too much information. It's very hard for normal users to evaluate the information quality. Typically, reputation systems are deployed to evaluate the information quality and filter spam. For example, in Stack Overflow, users can ask questions, answer questions, and cast votes to the questions in order to update their reputation scores. A higher reputation score means the user's questions and answers would be more valuable. We have many other reputation services, for example, Yelp, eBay, TripAdvisor. Here's a very simple example about a message board with reputation mechanism. We just wanted to use this example to illustrate how a typical reputation system works and our motivation. Suppose a newcomer, Alice, posts one message on this message board. This is Alice's identity. Because Alice is a newcomer, so her reputation score is 0. This is how many votes she received so far. In our example, 3 users read the message. So they really like the message. They cast positive votes to the message. In this case, the reputation system updates Alice's reputation score, so Alice's reputation score becomes 3. In the future, if Alice posts another message, so the new message would be attached to the reputation score, which is 3. For example, another user, Bob, posts one message. Unfortunately, 2 users do not like this message, so they cast negative votes to the message. In this case, the reputation system updates Bob's reputation, so Bob's new reputation becomes a -1. Reputation systems are very helpful to evaluate the information quality, but users really care about their privacy on the reputation system. In particular, people want to participate in these reputation systems anonymously due to the following reasons: sensitive topics, business competitions, and other personal concerns. There have been many investigations talking about why people care about their privacy in the reputation system. For example, a famous TripAdvisor reviewer, Peter Hook, explains his privacy concerns on the reputation system. Unfortunately, all the existing reputation systems have a very important privacy problem named the linkability problem. What is the linkability problem? Linkability problem means the user's privacy can be leaked by tracking their activities to their long-term identities on the reputation system. In our example, the attacker or a malicious reputation service provider can track Alice's activities because this information is maintained by reputation service provider, and all the users can observe this information. Even worse, note that this attacker might be the reputation system provider, so he can always track users' activities on the reputation system. In a recent measurement study, attackers successfully exposed eBay users' purchase histories by tracking their activities to their pseudonyms on eBay system. A funny story I heard from one of my friends this morning. He successfully tracked his advisor's purchase history on eBay system recent days. So researchers and business communities advocated anonymous reputation systems should be proposed to deal with the linkability problem. In an ideal anonymous reputation system, users and the reputation system providers shouldn't be able to link any user's activities to their identities. So some anonymous reputation mechanisms have been proposed. For example, e-cache-based approaches introduced anonymous electronic caches as users' reputation scores. However, this type of approach only supports positive feedback, which means malicious users cannot be punished. In addition, the e-cache-based approaches do not support the diverse reputation algorithm. Another type of existing solutions use blind signature-based approaches. Similarly, they also do not support the negative feedback. And the blind signature needs to depend on the centralized bunker. In addition, for both of the existing efforts, they depend on the computationally expensive crypto primitives, which means they are not practical. The goal of this work is to propose the first practical tracking-resistant anonymous reputation system. Our system allows diverse reputation algorithms while maintaining the unlinkability and anonymity of the user's activities. Furthermore, we do not need to trust any centralized third party, and our system should be scalable to large size of user site. So let's go back to our previous message example. This is exactly the linkability problem in existing reputation system. If this message board deployed our anonymous reputation system, nobody in this scenario, including the reputation system itself, can track any user's behaviors. However, building such an anonymous reputation system is very hard in practice. The first challenge is the reputation update itself heavily relies on tracking users' behaviors to their identities. But now reputation system backend or maintainer shouldn't track any user's behaviors, and they still need to update users' reputations. So in practice, we say this is a paradox. The second challenge is, yeah, anonymous reputation system, no party can track any user's behaviors. So how we detect the malicious users? For example, a malicious user may cast a duplicate votes to the same message. So how we detect this bad person? In this paper, we present an AnonRep system which overcomes all the challenges we just talked about. In an AnonRep system, we have two types of members. We have many clients, which are the users of the reputation system. There is a small set of commercial servers maintained by different third parties. So the servers facilitate anonymous reputation service. An AnonRep system follows any trust assumption, which means we assume at least one server should be honest, but we do not have any assumption on the clients. Malicious servers and clients can behave arbitrarily. AnonRep members, including servers and clients, participate in a continuous series of rounds. In practice, each round might be hours to days. In each round, there are 3 steps: announcement, message posting, and feedback collection. For example, let's say each round takes 1 day. We can do the announcement at the beginning of this day, and many message postings and feedback during the day, and finally, we collect the feedback at the end of this day. The input of each round is a list named the reputation list. The first column of the reputation list records long-term pseudonyms for all the users in this system. The second column records the encrypted reputation scores of users. These reputation ciphertexts are encrypted by all the servers. The output of each round is another reputation list whose reputation scores have been updated according to what happened in the current round. The output list will be used as the input reputation list of the next round, and so on. Therefore, we say the key design of an AnonRep system is what happened in each round. We have 3 steps in each round. The first step is announcement step. So the purpose of announcement step is to assign one-time pseudonym to each user in the current round and recovers the reputation ciphertext to the reputation plaintext. Announcement step is performed by all the servers. So the servers in some sense transform the input reputation list to the fresh pseudonym list, like this. In the message posting step, users can post messages using assigned one-time pseudonyms. In the feedback collection step, servers collect received feedback and update users' reputation scores, and finally outputs updated reputation scores, updated reputation lists with the updated reputation scores, of course, in ciphertext. Let me show the detail of the design of each step. The main purpose of announcement step is to transform the input reputation list into a fresh pseudonym list. Remember, each reputation score in the reputation list has been encrypted by all the servers layer by layer. Each server is maintained by a different party. During the announcement step, each server individually performs a verifiable shuffle protocol. The verifiable shuffle is an existing crypto primitive. In particular, the first server first reads the reputation list. It uses a fresh secret to encrypt all the items in the first column. At the same time, it uses its private key to decrypt 1 layer from the reputation ciphertext. Because the reputation ciphertexts have been encrypted by all the servers, so the first server only strips 1 layer. Then the first server permutes the list and sends the permuted list to the next server. At the same time, The first server uses the verifiable shuffle protocol to generate a zero-knowledge proof to demonstrate it correctly performs all the operations. So the second server does the same thing as the first server and sends the permuted list with the proof to the next server and so on. So the final server outputs its permuted list. This permuted list is exactly the fresh pseudonym list. Now the reputation scores in the second column of this list has been plain text because all these servers have decrypted all the layers. In different rounds, servers have different secret to encrypt the first column. So one-time pseudonym for the same user in different rounds would be different. Only user herself can learn one-time pseudonym because only herself has the private key. This is the feature of the verifiable shuffle protocol. Now all the members enter the message posting step. We already have the fresh pseudonym list. This is the message board. Users can post a message. For example, Bob wants to post a message. So Bob generates the message hi using his one-time pseudonym and generates a signature for this message using his private key. So Bob sends this message to the upstream server with the anonymous communication system, such as Tor or Decent. If the signature verification succeeds, the server posts the message for Bob and attaches the corresponding reputation score for this message. Similarly, Alice also can post her message. In the feedback collection step, all the users are allowed to cast votes to the messages. For example, we have such a message board. If David wants to cast a positive vote to the message too, so he needs to generate a vote like this. The first part means this is a positive feedback. The second part is the identity of the message he wants to cast a vote to. The important part of this vote is the signature. We generate this signature using linkable ring signature. The linkable ring signature is an existing crypto primitive. Linkable ring signature means all the users construct a ring, and each of them has a private and public key pair. For a given message, one of the users can sign this message, and the verifier, which is the server in our example, can learn this message is signed by one of the users in this ring, but the server doesn't know who signed this message. So using linkable ring signature, we can hide the voter's pseudonym. Linkable ring signature can also avoid the duplicate votes. If a malicious user casts duplicate votes to the same message, it would have two same linkable ring signatures, so the server can detect this bad person. If a user casts votes to different messages, they would be signed by different linkable ring signatures because different messages have different hash values. Suppose the example message board receives votes like this. Because all the reputation scores here and votes are plain text, so AnonRep system can update the reputations according to any reputation algorithms. In this example, we just assume the reputation scores are updated by this way. So these two columns are exactly the updated fresh pseudonym list because the first column is the one-time pseudonym of each user and the second column is the updated reputation score. With the updated fresh pseudonym list in hand, all these servers perform announcement step in reverse direction to transform the updated fresh pseudonym list to the updated reputation list. So far, we have finished one round. With the updated reputation list in hand, we enter the next round. So far, I have presented the basic design of an AnonRep system. An AnonRep system also needs to address many practical issues. For example, intersection attacks performs optimization, misbehavior detection, and registration verification. Today, I just briefly talk about how we solve the intersection attack. For other parts, please see our paper for more details. Let me show you one example about the intersection attack. For example, there's a user who has very different reputation score than other users. For example, 100. This guy still can post messages across different rounds, of course with the totally different one-time pseudonyms like this. Unfortunately, this user still can be tracked by an attacker because he has so different reputation scores than other users. So in order to address this problem, we introduce a security-enhanced AnonRep system. First, we apply homomorphic encryption to encrypt all the actual reputation scores of users. In this case, no server can observe the plain text of actual reputation scores of users. Because we are using homomorphic encryption, so servers can still update the reputation scores of users. Second, each user is allowed to generate a zero-knowledge proof to demonstrate he wants to post a message with a reputation budget. The reputation budget is a plain text number smaller than his actual reputation score. Let's go back to our intersection attack example. If the message board deployed a security-enhanced version of AnonRep, so this special user can post messages with different reputation budgets across different rounds. So he can hide himself. This is the original example, so we can compare to different situations. Evaluation. We have implemented a working prototype in Go language. Our prototype is open source, and we heavily depend on another open source library, which is developed by our group in Yale. This is the computational overhead in announcement step. The green line is the computational overhead of each server during the announcement step. With 100,000 clients, each server needs about 1,000 seconds to perform the verifiable shuffle protocol. But because each round might be just many hours or one day, so 1,000 second announcement might not be a problem. So the computational overhead on the client side is very small. This is the computational overhead of feedback step. As shown in this figure, both of the operations, including generations and the verification, are similar cost. So the computational overhead increase linearly with the number of clients. For example, 10,000 client group, each user only needs 8 seconds to generate the feedback. Okay, in conclusion, AnonRep is the first practical tracking resistant anonymous reputation system. We support diverse reputation algorithms, and we do not need to trust any third party. So our system is scalable, and you can find more information from this link. This is my talk. Many thanks, and I'm happy to answer any question. Thanks.
Günzer, Cornell University. I really like the construction. It's very clever. I'm curious about one thing. So in your reputation, the definition of reputation, you essentially have a summation of upvotes and downvotes, kind of like Reddit-like schemes. But I think that, at least when we did the credence work on voting on peer-to-peer systems, we were doing this flow-based reputation scores, which are much less amenable to gaming. So, but then your anonymity maybe would get in the way of that. Can you say a few words about how a scheme like yours would work with sort of more flow-based, less hackable reputation systems?
This is a very good question. I very much like the credence work. So that was published 10 years ago in NSDI, right? Yeah. So our current prototype only supports the global reputation scores. So that means each user cannot have the personal reputation score. So to be honest, I have considered whether the current reputation system can be extended to the credence model, and we want to support more. But in that version, I found that it seems there are some leakage. For example, a malicious user may only cast a vote to a specific user and just track whether that user's reputation can increase or decrease. Because that malicious user also can have a personalized reputation list, right? So that's the reason I didn't choose to introduce personalized reputation score in the current reputation system. But of course, I think that's definitely a great question. I'm still thinking, whether we can support, the personalized, reputation system. But for current prototype, we only supported a global reputation score calculation. But I'm happy to talk with you offline. But this is definitely a great question. Thanks.
Raluca Popa, UC Berkeley, great work, I really enjoyed it. So I was wondering if we could use as an alternative zero-knowledge proofs, so the user could compute his own reputation and then prove to the server that he computed it correctly in zero-knowledge without actually revealing what he posted or voted. And the reason I'm asking this is that maybe in that way you don't need to trust the server at all, and you don't need a mutually distrustful model.
Yeah, that's a great question. Yeah, so for current architecture, we have to at least trust one server. But here's my answer. I try to investigate some zero knowledge proof to help users to generate such a proof and to show the server or the malicious server, okay, I have the reputation, or this is zero knowledge proof or something. But I didn't see a reasonable solutions in this direction. But maybe you know more, I think. But I was trying to investigate this work, but to be honest, I didn't find the suitable way to do this thing.
Have you considered set intersection zero knowledge proofs? Those are the faster ones.
That's a great question. I have thought that way. But I failed. so I think maybe it's possible. I work on something on the intersection protocol, but yeah, I will definitely think more about that way. But I'm not sure. Yeah, but definitely that's a great direction. I think is to extend this version. Yeah, thank you very much for your question.
Hi there, Luis Pedrosa, USC. So I am by no means an expert in this field, so this might come out as a stupid question, but I suspect that this is not resistant to collusion if all of the reputation tracking services collude all at once, at which point it would essentially become a hidden centralized service. But how resistant would it be to only partial collusion? So if you could guarantee that they wouldn't all collude, does it need 50% plus one? Does it just take two to collude, and all of a sudden you get enough information to de-anonymize the user?
Can you repeat that? Sorry, I think I may miss something.
So I'm asking about collusion on behalf of the reputation tracking services. How much collusion does it take to de-anonymize a user? Do you need all of the services to collude, or just is two enough, or does it have to be a majority?
Oh, so in current design, we need all.
So all it would take, for example, to resist a national security letter would be put one of them in Russia and one in the US and...
Yeah, because that's a trade-off between the security and the practical performance, right? Because if you have much more users, so sometimes you lose some performance, but you can guarantee more security. But again, my answer is that depends on the concrete application scenario. But
so all of them need to collude.
Yeah.
Thank you.